All right, continuing our delve into econometrics. We just talked about these alternative models, right? These logarithmic models, and we also talked about what? We also talked not just about those, but about this kind of bigger idea of like marginal effect and interpretations or utilities for coefficients, right? So we're going to take these ideas and we're going to apply them in a different setting as we move on to a discussion in what I'm going to call advanced hypothesis testing. So in economics and realistically any kind of business context, we often want to test various theories, right? Testing those theories, of course, often in a statistical situation equates to hypothesis tests on combinations, possibly linear, or as we will see down the road, possibly nonlinear combinations of parameters. These tests, right? Tests on combinations of parameters can be done in a lot of different ways, using a lot of different software packages. But in SAS, they're particularly easy to use using something called proc model. So let's go ahead and look at an example. So this is data from quote Big Andy's Burger Barn. Um, Supposedly real data, but surprisingly a fictitious name. Um, this real life fast food franchise set a variety of prices in units of $1 and advertising expenditures in units of thousands of dollars in 25 markets to observe their effect on sales. That's in units of thousands of dollars. Okay? So that's our context. And here are the questions that our boss asked us. They asked us 3 questions. First off, does advertising expenditure influence sales? If so, how? Do the prices of our Andy's Big Burgers influence sales? If so, how? And the third question, is advertising paying for itself? Okay. So here's our model. Um, at least it's a starter model, right? And so our starter model looks like what? It's a multiple linear regression model. We have two independent variables now, right? I use x sub p for price. I put beta 1 here, but I think I use beta p in a future slide. So sorry about that. And then here I have x sub a for advertising, and beta 2. I think I might call it beta a. So just to really drive home, right? Now one of those betas is associated with our price variable. One of those betas is associated with our advertising variable. Now, if we were to take those questions, right, posed to us by our boss an alleged non-statistician, and we tried to translate that into, right, something statistical, right, maybe a hypothesis test. How would we write that out symbolically relative to, right, the model we expressed in the previous slide? Well, our first question, right, does pricing impact sales? Well, that's really essentially just doing a hypothesis test of whether or not the coefficient for pricing is zero or not zero. Our second question, right, does advertising impact sales? We're really just looking at the significance of that advertising variable. And then the third question is maybe like a little bit deeper than what we've looked at, say in 512, right? does advertising pay for itself? So what would that look like, right? That would basically look like a coefficient of 1. Do we agree with that? Right, we would want that coefficient to be either 1 or I guess more ideally larger than 1, right? Because the coefficient is basically saying for every $1 we spend on advertising, our sales increase by blank. So, I mean, we want if it would be great if we spend $1 on advertising and sales increase by $2, right? That means that we got some value for our money. If it was exactly 1, then it's like we spent $1 and we gained $1, we kind of broke even. If the coefficient is something like 0.5, it's basically saying for every dollar of advertising we spend, we make 50 cents in sales. So it's like we actually have overall lost money, right? And so really what we want is, right, another way of thinking about this is we really want to do a hypothesis test of whether or not the coefficient for advertising is equal to 1 or whether it's not equal to 1. To be honest, I guess we really want to know if we want to know if it's doing well, we would really want to know if it's greater than 1. That would be a one-sided test, and right, we could do a one-sided test just essentially by having our p-value. Right? Remember the p-value for a two-sided test is 2 times that of a one-sided. SAS by default does a two-sided test, which is why I wrote the thing out this way. Now, proc model and most SAS procs test whether things are equal to 0. So I have to kind of rearrange things a little bit. And so a hypothesis test of whether or not beta A is equal to 1 is equivalent to a hypothesis test of whether or not beta A minus 1 is equal to 0. Do we agree with that? And again, I'm re-expressing it this way algebraically because ultimately that's the way that SAS is going to kind of expect me to kind of feed it into it. All right, so here's proc model. So proc model, we start with a label statement. And the label statement, we're just going to assign, we're going to have a number of parameters. These are the things that we're going to perform our tests on. We can give them names. We don't have to, but we could use the label statement to give them names. So, right, the beta naught is our intercept. B1, right, is price. So I'm being very explicit there. B2 is the coefficient associated with advertising. I then write out, right, my model. So my model is that sales is equal to, I'm writing out the linear model, and then I use the fit statement to fit that model. Once I fit the model, I can perform tests on any particular combination of coefficients, right? So ultimately, questions 1 and 2, we're just going to look at the significance test of beta 1 and beta 2. But to do that question for the third question, right? Does advertising pay for itself? I want to do a test of beta 2 minus 1. Again, I'm always basically the estimate statement. I always put the left-hand side of whatever equation should equal 0. Okay? So I run this code and I see the following output, right? So a little bit similar to like a proc reg, a proc GLM. It kind of focuses more on, right? I get a little bit of an overview there, the MSE, the R squared. Um, I get my hypothesis test for the coefficients, right? And so in particular, I see that my price coefficient is what? My price coefficient is about negative 8-ish. So it's basically saying, um, right, for every $1 we increase in price, we expect sales to decrease by about $8,000, right? So that I think that makes sense, right? It's basically saying people don't like expensive burgers. If we make our burgers pricey, we're going to lose customers, right? And that sort of tells us how many customers we might expect to lose. That's significant, right? So price does affect it in a negative way. Does advertising affect sales? Well, again, that p-value is highly significant, 0.0080. The coefficient is about 1.865. I'll call it 1.9. I guess maybe we can call it 2 if we want to just kind of be real lazy. And so 2 is saying what? It's saying that for every $1,000 that we increase that we spend in advertising, right? We expect our sales to increase by 2,000, right? Um, so all right, so that is an impact. Now, the third question is, does advertising pay for itself? So, right, that 0.0081 is essentially saying like, yeah, our advertising coefficient is significantly different than 0. But realistically, right, in a business setting, in a business context, we're actually interested in whether or not it's significantly different than 1, right? And that's what the next test does, where it says, does advertising pay for itself? That's testing whether or not beta 2 is equal to 1, or alternatively, whether their difference is equal to 0. We find that p-value is 0.2108. So it's basically saying that we don't think that the advertising coefficient um, is significantly different than 1, which means that we don't have statistical evidence to suggest that advertising is in fact paying for itself, right? Our point estimate is more than 1, but if we were to make a confidence interval, that confidence interval would include 1. That is, the lower portion of it would be less than 1. That is, right, we're 95% confident that that coefficient is somewhere between something a little less than 1 and probably something a little bit more than 2. All right. So here I just made that explicit, right? So question 1, yes, price impact sales. As we increase by price by $1, we expect sales to decrease by 8,000. Right? Yes, advertising impacts sales. If we increase advertising by $1,000, we expect sales to increase by uh, almost $2,000. And then the third question, right, like we said, no, because the p-value is like zero point 0.2 something. There is not sufficient evidence to conclude that advertising pays for itself. All right, so that's kind of like a starter model. We could ask a whole bunch of questions using proc model. And I know some of this stuff we could do just kind of I, I think just like using our intuition. But we'll see, like, right, one of the nice things about SAS is we actually will get things like standard errors, and we'll get at least the pieces that we need if we wanted to do a confidence interval, for example. Right? So for example, if management asks some follow-up questions, right? Here's a couple possibilities, right? What change would we expect if we increased advertising by $800 and we dropped the price by 40 cents? And then, is dropping the price by 20 cents more effective than increasing advertising by $500, right? So let's take a look. Right, and here we go, right? So um, Right? So beta 1 is price. So we're really basically saying what happens if, right? So our first question, question 1, what happens if we decrease the price by 40 cents, so negative zero point 0.4, and what happens if we increase the advertising by 800? Our units are thousands of dollars, so 800 is zero point 0.8. Okay. The other question is a 20% or is a 20-cent decrease in price equivalent to a $500 increase in advertising, right? Again, remember this, the way I'm writing this equation for this question 2 estimate is we're really testing whether this negative zero point 0.2 beta 1 minus zero point 0.5 beta 2 is equal to 0. And so if I rewrite that, right, it looks like I'm testing the hypothesis whether negative zero point 0.2 beta 1, i.e. decreasing the price 20 cents, is equivalent to positive zero point 0.5 beta 2, right, which would be the equivalent of increasing advertising by $500. All right. So we can ask, we use proc model to fit this, and then we can look at the output. So here is our output, right? We have our two tests there, question 1 and question 2, right? So question 1 is basically saying, right, what do we expect to happen? We if we were to decrease sales, or sorry, decrease price by 40 cents and increase advertising by $800, we would expect, right? We would expect sales to increase by, right, that 4.65, but remember this is in units of thousands of dollars. So, right, $4,653. So that's what we would expect to happen. Now again, like you don't need SAS to do that calculation. And we're really essentially just doing negative zero point 0.4 times beta 1. So not times the negative 0.79 and zero point 0.8 times beta 2, so that's 1.86. You can do that in a calculator. But we're getting a p-value, a significance test, so we could test whether it's significantly different than, say, some number, maybe some historical value, for example, or whatever, maybe some target goal that we set. And we could also take things like the standard error and the t statistic, and we could build a confidence interval, which would allow us to, right, more explicitly state the inherent uncertainty with that estimate, right? So there is a lot of added value to what proc model is providing us, right? So question 2 is a 20% decrease in price equivalent to a $500 increase in advertising, right? And here, right, our hypothesis test is non-significant, right? Which means that essentially negative zero point 0.2 beta 1 is equal to, right? We fail to reject the null hypothesis that negative zero point 0.2 beta 1 is equal to positive zero point 0.5 beta 2. And so we fail to reject the hypothesis that they're equal. So we would think that, right, that it's roughly, that doing that is roughly equivalent, right? Even though in terms of a point estimate, it looks like we would get a little bit more sales from decreasing our price. When we calculate like just the noisy uncertainty of like the sampling process, right? That slight difference of 0.65 is not large enough that we think it's convincing that like that these two approaches are statistically different, right? These two approaches of either reducing price or increasing advertising. Yeah, so conclusion, For question one, our estimate is 4.653, meaning that we would expect sales to increase by $4,653, significantly different than zero. And like I pointed out earlier, right, we could use the standard error to make a confidence interval for this. Um, and or do hypothesis tests to see whether it's significantly different than some benchmark or target goal. For question two, we observed that dropping the price by 20 cents will generate $650 more in expected sales than increasing advertising by $500. The p-value though was not significant. So the two approaches are statistically equivalent or not significantly different. All right. All right, so that's just kind of like a basic model, right? How could we improve the model? And I know there's a few different ways we could answer this, right? We're pretty smart now when it comes to statistics. We could add interaction terms, for example. That's a possibility. We could even add some logarithm terms, right? We learned how to do that recently. And those are things that we could, I would encourage you to look at. But for this example, and particularly for like larger multiple regression models, it's probably more common to add higher order terms like these polynomial terms than it is to add, right, these different logarithmic terms. So let's for now, and again, the data set is on D2L if you want to play around with some other models. But for now, let's take a look at what a quadratic model would look like. And for simplicity, I'm just going to focus on looking at a quadratic model with respect to advertising, right? Somewhat arbitrary. If you want to play around with the data and you want to also try a quadratic term for price, feel free to test that out yourself as well. Yeah, so here's a quadratic model with respect to advertising, right? So yeah, so here we go. I add a third term, which is the square of advertising, right? So we could see the code extends pretty easily. I have to define or label a B3, and then I just add it to my fitted equation. So here we go, right? This is now my new equation. So I got the 109.719 and the price. Um and then right the I guess the linear portion of the advertising polynomial and the quadratic portion is the negative. That's the part we added, negative 2.7 whatever. Notice that quadratic term is significant. So adding it has improved our model. All right. Now I have some other stuff there. Question one, question two, question three. I haven't asked the questions yet. I just wanted to show real quick what our quadratic model looks like. And then I want to show you like a graph of this quadratic model. Um so look, remember our coefficients, right? I'm going to focus on just the quadratic part, which is the advertising. So I'm going to kind of like for now, I'm going to focus just on that. So I'm going to eliminate price. So zero that out. And we would have what? 109.719 plus 12 times advertising minus 2.77 times advertising squared. So what would a graph of that look like? Well, here's a graph right here, right? And so first off, so a couple things, right? You can graph. I think in Stat 511 you learn how to like make graphs. In your R programming class, you've probably also learned to make graphs in R. And that's fine. I actually considered doing that in this PowerPoint, but I was pretty confident that there was some applet out there that I could just like Google and it would just I could just type in the equation, it would just graph it for me like super quick and super easy. And that's all I did. I just went to Google, I typed in whatever, plot my equation easily, and it gave me this Desmos link. I had never used Desmos until right now. And then, yeah, I just typed in the equation. I just typed it in, y equals blah, 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 and it made this little graph for me real quick and easy. So, whatever. Shout out to Desmos. Hope I'm pronouncing your name correctly. Apologies if I'm not. So again, right, one of those things, work smart, not hard. Anytime you kind of just like you have an equation, you're trying to visualize it in your head. I mean, you could do it very easily. There's lots of resources out there that whatever charitable people have made public for people such as you and I. So again, a quadratic model, it's got a negative coefficient for the x squared term, so it looks like a frowny face. And so what do we see, right? In this particular data set, so look at the x-axis, right? The x-axis is like it goes from 0 and then 5 and then 10 and then 15 and 20. More finely than we have like 1, 2, 3, 4, 5. That's kind of like the inner part of these little graph squares. Um, in the data set, the smallest value of X, this is advertising, is 0.5. 0.5 corresponds to $500. And the largest value is 2,000. That corresponds to a value of 2. So this thing got graphed for like, it looks like this particular, I zoomed in on the graph from what, like -1 to 5. But our data is all between like, is all between like positive zero point 0.5 and 2. And so if I focus on that range, like what do I basically see? Right. I wanted to plot this because I wanted to like emphasize one of the things we talked about, right, in that previous lecture, which is this idea of like marginal effect. Because what do I see? I see that this thing is increasing very steeply, but as it gets closer and closer and closer to its peak, right, it does start to flatten out. Its steepness diminishes, right? I like to use the term like diminishing returns. What is this saying in the context of the problem? I think it's a very intuitive thing that it's communicating. It's saying that advertising has diminishing returns, right? That is like the first $500 that you spend is maybe going to generate a lot of sales because you're basically going from like zero awareness to, to potentially national awareness. And if you pay another $500, well, now maybe you're reaching a few more people. And so your sales are going to increase, but maybe by not quite as much. Does that make sense? And so the idea is like every additional $500, it's still generating sales, but not as much sales. Right? The value of that advertising is diminishing. And we might imagine like at some point, like you stop getting any value out of it, right? That is, at some point you've like spent so much money on TV and YouTube ads and billboards and everything else that like that the whole world is aware of you, and there's no more awareness to build. In fact, who knows, at some point you're putting so many commercials out there that you're starting to annoy people and you're starting to generate negative sales because of it, right? You've over advertised. Does that make sense? And so this is that idea of like marginal effect in this context we can think of is this concept or this idea of like diminishing returns, right? That's what I wanted to try to demonstrate with this graph. Okay? Now let's try to actually answer some business related questions, right? Some questions that might help us, right, get to the bottom line. So here's some new questions from new management. If in fact we have diminishing returns, then what is the marginal effect of advertising on sales when advertising is 500? That's the lowest value in our sample. So maybe that's like the lowest we might consider doing. What's the marginal effect of advertising when advertising is 2,000? That's the largest value. So maybe that's like the largest number we would consider, right? We're going to expect the number, again, let's stop and think. We're going to expect the marginal effect to be larger at 500. Do we agree? That's the whole idea of diminishing returns. It's going to be smaller. There's going to be a smaller net gain after we've already invested $2,000 in advertising. And then the third question, I want you to maybe pause this and think about it. Like, how would you answer this? Like, what's the optimal level of advertising? What's the optimal level of advertising? That is, at what point should we stop? All right. So I say question one and question two should be straightforward. I mean, straightforward is maybe a bit of a stretch, but we did solve, right? Last lecture we solved the equation for the marginal effect of a quadratic equation, right? That's essentially just the derivative. And remember, the derivative was beta 1 plus what? 2 times beta 2 times x. So we just basically want to solve for the marginal effect at x equals 500 and x equals 2000. What's the derivative at these two values, 500 and 2000? The third question, does this make sense? We basically want to solve for when the marginal effect is at $1, right? So we have this idea of diminishing returns. That is, for every $1 we spend in advertising, how much do we expect to make in sales? And, right, the impact of advertising is getting less and less and less and less as we spend more and more and more and more. We want to stop spending when that marginal effect is at 1. Do we agree with that? That makes sense, right? Because as it's getting smaller, if it's smaller than 1, then advertising is now like losing us money, right? Again, if that marginal effect is less than 1, it's basically saying that we're losing money as we pay for additional advertising. Like, it is gaining us customers still because it's positive, but that gain is not sufficient to offset it's no longer sufficient to offset the advertising expenditures. Okay? So here we are, right? I fit this. I now have my 3 questions, right? I could create values in here. So advert 1 is 0.5. This is going to be, right, we want the marginal effect at 500, right? Remember, 500 is 0.5 because our we're in units of thousands. And we want to also do it at 2000. That's just going to be an advertising of 2. So question 1 and question 2, I solved in the previous lecture what the marginal effect, what the derivative is, and that's beta 2 plus 2 times beta 3 times x. I'm plugging in an x of 0.5 and I'm plugging in an x of 2. And that'll tell me the marginal effect at those points. Question 3, what's going on here? Well, I really want to do what? I really want to take that marginal effect, which is beta 2 plus 2 times beta 3 times x. I want to solve for when that is equal to 1, right? So again, it's just an algebra problem. Write that out. Write out beta 2 plus 2 times beta 3 equals x equals 1, and then solve for x. If you solve for x, what are you going to do? You're going to subtract beta 2 from both sides. So you'll have 1 minus beta 2. You'll divide by 2 times beta 3. So, right, the implication is that x is equal to 1 minus beta 2 divided by 2 times beta 3. And if I want to solve for that, well, I can use the estimate statement to solve for it, right? So the point estimate solves for it, but I also, of course, have p-values and I can generate confidence intervals, right? So I can do a lot of other things as well. And so we go to the next slide, right? And we can answer our different questions. So question one, when we've only spent $500 in advertising, the marginal effect, the marginal gain is from that point on is like for every $1,000 we spend, or for every whatever, if we want to rescale it, for every $1 we spend, we expect sales to increase by $9.4. So we're still getting a lot of value at a advertising budget of 500. We're still getting a lot of value. $1 of advertising is getting us almost $10 of sales. So that's great. Question two is, well, what happens after we've spent $2,000? And at $2,000 now, right, every additional $1 is generating $1.08 of sales. So we can see, right, at x equals 2, at an advertising of 2, which is equivalent to $2,000, we're almost at that point where it's no longer worth it. Our returns have diminished very close to 1, but not quite. If we want to solve what is the value of x where that coefficient is exactly 1, well, that's our third question. Our third question tells us, and again, concept check. That should not be surprising that this number is just a little bit more than 2. 2.01434 is the value of x. It's the value of advertising such that the marginal effect is exactly equal to 1. That is, if we were to pay any more advertising beyond that, our net gain is going to be less than the money we're putting into it. So essentially it's basically saying, right, that we should be spending $2,014.34 in advertising, and that's where we should stop. Because at that point, we're no longer generating profit, right? We're instead generating debt or loss. Yeah, pretty cool, right? Yeah. So there's our answers. And then finally, if you were to write it out, right? I know the output always said like nonlinear test or nonlinear combinations. Really, the first nonlinear combination, which if you kind of look at that equation, we had what? We had like a beta 2 over a beta 3, right? That's what made it a nonlinear hypothesis test, and that's where proc model is actually really handy. It's one of the few procs that could handle or implement these nonlinear hypothesis tests. All right. All right, so that wraps up, I think, hypothesis test. Hopefully, gives us a lot to think about, maybe something to dream about. I'll go ahead now and put together some assignments for you to kind of implement and practice some of the things that we've talked about. All right, so that's all I got for right now. See ya.